Today we're going to talk about another type of potential energy, known as the elastic potential energy. Pretty much all materials will bend and resist changing shape or deforming to a certain degree, and then when you release them, they'll go back to the original shape. They're said to be elastic. But there's a natural state that they have, and then you must apply a force to deform them or stretch them. So if this is the natural state of the rubber band, then I stretched it a distance d. And when they're in this elastic region, they store the energy as potential energy. And when you let them go, they release that energy and it becomes other types. But if you go beyond that elastic limit, then you're no longer storing energy. For example, when you stretch your rubber band and you break it, that energy is released. When springs are stretched, they'll store some of that energy in elastic energy, but some of it is gone to what's called deformation energy. When you pull an archery bow back too far, it can snap. And paper, believe it or not, is elastic. But if you bend paper a little bit, it'll bend back to its original shape. But if you fold it too sharply, then it'll remain folded and it's gone beyond the elastic limit. The equation for the force that's involved here, this is known as Hooke's law. The force of the spring is equal to minus kx. Kx is a spring constant, and it's basically how stiff the spring is. Is it really, really easy to stretch, or is it very tough? If it's difficult to stretch, then it's got a large k constant. And x is how far you've deformed it away from the natural shape of it. So most of the time you're going to see this equation, you're going to see it with this negative in front, and we'll talk about why that negative is there. The equation sheet for AP Physics gives it to you in this absolute value form, just basically taking away the negatives, and then it doesn't really matter. The reason that that negative that is there is, let's say I stretch a spring to the right and I give it positive displacement. Okay. The string, and here it's at its natural state, its natural length. And here I compress it, and it's going to have a negative displacement. So now the direction that the spring is going to pull or push. So when I stretch it to the right, the spring is going to pull to the left. And here there's none. And here, when I push it to the left, it's going to go to the right. So the reason that that negative is here is so that if I have a positive displacement, then my force is going to be in the negative direction. That's really it. And if I push it to the left and I give it a negative compression, a negative displacement, it's going to have it's going to push back in the positive region to the right. So that's the only reason that's there. Basically, it just is a way of saying that when you stretch a spring, it pull back the opposite way that it went. So not a big deal. So, and the K again is the spring constant. X is basically in here because the further you stretch that spring, the harder it's going to pull back. So when you stretch it back a little bit, there's a certain amount of force that's trying to pull it back. When you stretch it further, that spring force is going to increase. So basically, the more you stretch your rubber band, the harder it pulls back. So here's a basic problem. A spring is naturally 0.5 meters long. When stretched to 0.8 meters, what force will the spring exert if the spring constant is 6 newtons per meter? Well, the original length of the spring is 0.5 meters. It's stretched to a total length of 0.8, which means that the distance stretched, or the displacement in this case, is equal to 0.3 meters. Now, plugging that into Hooke's law, the spring constant equation, so that's going to be K is going to be 6 newtons per meter, and that's what the spring constant is measured in newtons per meter, and times the displacement, which we said is 0.3. That's how far it's stretched. Multiplying it, and it's 1.8 newtons. So, and the spring constant basically means for every meter that you stretch it, it's going to pull back with 6 newtons of force. We only stretched it, a third of a meter ish, so we only got about a third of that in terms of the force back. It's important to note that this relationship is linear. If I put twice the force on a spring, it's going to stretch twice as far. If I were to graph that as a function of force and x, you would get a linear relationship because with a slope equal to k, slope equal to k. That's why that spring scales are able to have their scale measured linearly, because if you put twice the weight on it, it's going to pull twice as far. So that works out nice. Going back, if you took principles of engineering, I'd like to relate it a little bit to that. So remember, this is our elastic region. So this is how far we've stretched it, or how much strain we're putting it under, how much force that it's under. And this is how much it's elongated, how much it's stretched. Stress versus strain curve. And there's this linear region, okay, where you stretch a piece of metal, or anything for that matter, where it's linear. And when this is known as the elastic region, when you release it, it goes back to its original length. Now, if you stretch it beyond that, you get what's called plastic deformation, and it never recovers from that. Once you go beyond the elastic region, you get into plastic, and we lose energy in the form of deformation energy. So this linear region, though, is where we're going to be focusing on in this class. So remember, if we had a force versus distance curve, we could find the area under it, and that would be the work done to do that. Well, this force is 0, and here when we're at a distance x stretched, then the force that the spring is going to pull back is a magnitude of kx. So when we find the area under this curve, it's multiplied x times kx, and which we get is kx squared over 2. So the work done to stretch the spring is kx over 2. That's also equal to the amount of energy that the spring stored it, assuming that there was no plastic deformation. So this is the next equation that you need. The potential energy stored in a spring is equal to kx squared over 2. Now note this is similar to the equation for the force, which is kx, but this is k. They're different things, and they're different equations. If you like to go all calculus-y, you can throw a little calculus at this. It's the integral of kx dx from 0 to x, and you'll arrive at the same thing. So again, just a side note, the force that you have to apply to stretch a spring goes linearly with the distance stretched. The energy goes up exponentially because it's kx squared. So keep that in mind. There might be a multiple choice question along those lines. Who knows? If not, I'll have to put one in. So the string of a bow is drawn back 0.5 meters, and it takes a force of 100 newtons to keep it there. What's the spring constant, and how much potential energy does it have? Well, the force is equal to 100 newtons. That's equal to the spring constant, which is what we're trying to look for, times the distance stretched, which is 0.5 meters. And we get that the spring constant is equal to 200 newtons per meter. Now, to figure out the potential energy, we need to use the new equation. U sub s equals kx squared over 2. So k is equal to 200. X is 0.5. Don't forget to square it. And divide by 2. And we get 25 joules. So that's the spring constant, and that's the energy stored in the spring. Now, if I were to stretch it twice as far, I would have twice the force, because force is linear, but I would have 4 times the energy, because the energy is proportional to the displacement squared. So keep that in mind. So video clip. I guess this is probably going to be going past the elastic limit. Be my guess. What happens if the bow fails on you? Might as well watch it. I don't know if you can hear the audio on this, but it's a little bit funny. Um, for those of you unfamiliar with bows, the arrow is supposed to fly, not the bow. Um, so that was demonstrating poor skill there. Okay. Um, how much potential energy does a 150 kilogram rock gain if it was moved 2 meters up on a planet with no gravity? Well, the potential energy equals U sub G equals mgh. And if G is 0, then U is going to be 0 as well. So that is not going to work. So there's no force that you'd have to exert to elevate it. You would also be doing no work, and you would also be storing no energy. Um, so just to kind of keep in mind, an object only gains potential energy if the work was done against a force, okay, and if that energy can be stored in a way that it can be used. Okay? Work done against friction is not stored as mechanical energy, but is converted to heat or thermal energy. Probably the more correct way of saying it. So friction is not what's called a conservative force, which means that energy is not conserved when you talk about when you have friction involved in your system. Okay. How much work is done to push a 35 kilogram object up a frictionless ramp on Earth? Here we've got this windy ramp, and it changes the elevation. So we don't really know what the angle is of this, so we can't use a free body diagram because the angle changes. But we can use what we just learned about as far as energy goes. So if we want to figure out the work done, all we have to do is figure out how much energy the thing stored. Now it said it's frictionless, so we're not going to lose any energy. So we're going to use work equals the change in energy, and the energy is going to be stored as gravitational potential energy, which is mgh. So the work is equal to 35, its mass, times 9.8 times 25 meters, which is the elevation. So 88,575 joules. The basic problem, basically work equals the change in energy. That's something I want to try to beat into you guys. Work equals the change in energy. So if we had two magnets and they repelled each other, could they store potential energy? Which way would you move the magnets in order to store potential energy if they repelled each other? You would have to push them towards each other as they repel each other, and that energy would be stored as magnetic potential energy. And if you flipped one so that they attracted, then you'd pull them apart, and that would store potential energy. Where there's no equation that we're going to deal with for potential energy of a magnet, but just throwing it out there. Now, when we talk about temperature, temperature indicates what about the atoms in a substance? What happens to the atoms in a substance as it gets warmer? Um, um, okay, I guess we're not going to watch that, but well, they move faster. So what kind of energy goes is increasing when they start moving faster? The kinetic energy. So temperature indicates the average kinetic energy of the particles in a substance. It's only average because the atoms are all moving at different speeds, but there's like an average speed that is what the temperature is. Okay.